Welcome to our class. Today we want to continue with our discussions on Noir. This time we shall look at hashes, private inputs and hashes. So how do you hash some message? And that is what we will be looking at. And then after hashing, what we want is, for instance, the verifier can see what the output is, but the input will still remain secret. Only the prover can know that what the input was. You know, if you have the hash, you cannot generate the input. You cannot go back. You cannot get the reverse. That is the advantage of hashing. Now, so what we'll be doing, just a summary in today's lesson, we need to understand the difference between public inputs and private witnesses. Of course, this we already know, but just as a reminder, and then we need to learn how to hash. And then after that, build and run a circuit that checks SHA-256, the pre-image that what you put inside, that is the input that you put, and then what public hash do you get? Now we'll run proof generation and proof verification. If we get time, we can go to that. The prerequisites to today's lesson we already have. We've installed most of the things we require. But any person who wants to do the same and has not installed, then I've again listed what needs to be installed before you can do what we will be doing practically. So one needs to have installed Rust. Of course, you need to have installed Noir and so many other things. We've already listed what needs to be installed in our previous lessons. But again, I've repeated them here. Part of what you require is Raster toolchain, which is stable, and how to install is by using curl. You can use curl to install, as we've always done. So you can use this command to install. If you want to install Node.js, you can also use sudo apt install Node.js. Now you can also want to install okay, for cargo, I've just placed, but I think this is the correct way to install it. You may just want to confirm, and so on. Noir, you may want to confirm. The current way, the modern way of installing. Now, so after you've installed the requirements, then we need, first of all, just to remind ourselves about what we mean by public inputs and private witnesses. So public inputs, as we've always said, these are inputs which will be visible to everyone, both the prover and the verifier. So the prover knows it and the verifier knows it. So in our today's lesson, the public input will be the hash. The hash will be public. So the verifier can see the hash and the prover can see the hash. Of course, the prover is the one hashing. And then the verifier gets to see the hash. But now we have a secret input, and that is what we call private witness. Only the prover knows what it is. The verifier does not get to know what it is. But the verifier can see the relationship. So the hash, supposing the secret is X, so the verifier is able to see H of X. That is the hash of X. But then from this, you cannot go back to get what X is. So the verifier cannot know what X is. It's only the prover who knows. So this is the hash of X, which is public. Therefore, the verifier knows it, and the prover also knows it. So therefore, in today's lesson, the hash will be public, and then the private will be our pre-image. Pre-image is just the X that you are hashing. What you are hashing, you can be hashing a word, a number, or something. So whatever you're hashing is what we are calling the pre-image. Now, just before we look at how to do hashing, of course, you can hash using any, it's not a must, it has to be hash 256, SHA-256. There are so many ways of hashing. There are so many means. SHA-256 is not the only one that we can use. But now, why do we hash? That is what is important to us. Now, one, hashes let us publish short, fixed size commitment to a secret. So the secret in our case would be password or anything, even data and so on, can be our secret in this case. So you want to hash it just for security reasons. It's only you who know your password is, but the other person will not get to see it. Will only be seeing the hash. And this is what happens in many cases, especially even in banks. When you're asked for your password is never stored. What is stored is the hash. So every time you come to the bank and you're asked to input your password, you input, but after inputting, what happens is it's hashed and then mapped to the one that was stored to see if they are the same. If they are the same, then it's verified that it's a proof that you are the owner of the password. If it doesn't, and a very small thing would change what the hash becomes. A very small, even a comma, even a space would change the hash. So in ZK circuit, the prover demonstrates that I know X such that the hash of X is the public hash that the verifier knows without revealing X. So just demonstrating that I know this X, such that when I hash it, the result will be the same as what you have as public hash. That's what I said. The example I've given, for example, the example of the bank. You go to the bank today, or let me say even Even when you are opening your email address and you're asked to input your password. So you input your password, ABCD. This is not stored, so the system does not know what you input. Once you input this, it's just hashed. So you get the hash of ABCD is what is stored. The hash of ABCD is what is stored. So this is what is stored in the system. So when you come next and you're asked to input your password again is hashed. And then we want to see whether the result that we get when we hash your new password is the same as the public hash that we have. If it's the same, then you have proved you know your password. So that is what is happening in this case. Bullet number 2 just saying that in ZK circuit, the prover will want to prove that or demonstrate that he knows a certain value X such that the hash of that X is a public hash, what is common, what is known. In real world uses, I've already mentioned some, but of course, we do that in password proofs, in Marco tree membership, in commitment for voting, credentials, nullifiers for spend once, tokens, and so on. So there are very many ways it's applied. This knowledge is applied. So when you're writing, you just need to know. You're writing a circuit, you just need to know for what application am I doing this? And then you tailor it in that direction. But the way you write it is just the same thing. So just a few changes so that it now performs the function you want. If you want to do it for password proof application, just tailor it a bit. If you want to do it for Marco tree membership, just tailor it a bit, but the way we do it is almost the same. So a verifier therefore, after the prover has done input the value and it has been hashed, so the verifier can now check a pre-image relation without learning the secret. So just checks the relation. You've just input X. So the verifier wants just to see whether the value you get as the hash is the same as the public value he has. But now he will not learn what an X was. That's the advantage of this hash, is that, such that you cannot retrieve X from the hash. You cannot retrieve X. You can only compare and see that when this prover inputs that X, the value I see is the same as the value stored as the hash. So once the verifier checks that, the proof is sufficient to convince the verifier that the circuit constraints hold, including the equality, such that the hash of the preimage equals the public hash. So the proof is supposed to convince the verifier. So the verifier, once is convinced, that is okay, but he will not learn what the preimage is. So doing this preserves privacy while at the same time enabling authenticity or commitment checks, or authentication and commitment checks. So it enables that. Now, how does it hash? How does it hash? The way I've seen is when you input your value X, that's secret, it's first of all converted to a field. That's the first thing that will happen. It will first of all be converted to a field, a number. So let me say you entered ABCD. So A will be converted to a number using the ASCII mapping. It's called ASCII. ASCII. I don't know whether yes, I think it's this. So A will be converted to its ASCII equivalent. B will also be converted to its ASCII equivalent. Let me assume that the ASCII equivalent of A is 70, although I'll see what the exact one is. And let me also assume the ASCII value of B is 81, just assuming. And then the ASCII equivalent of C, let me say 63, just an assumption. And that of D, let me say is 50. So what is happening is that what you entered is first of all converted to its equivalent field values. It's these field values that will then be hashed. That is when you're writing the Noir circuit. Although when you're looking at if you're doing using Rust, it will just be automatic. This goes straight to the hash. This goes straight to the hash. But when you're writing the Noir circuit, then this will first of all be converted to fields. Then the fields will then be hashed. That's how that will be the format. That's how it will move from what you input, the value X, to the field equivalent, and then from there, the hash. So it's slightly different from if you're writing Rust to just be straight away in Rust. But of course, in Rust, it will not be doing zero knowledge proof. In Rust, what it will be doing just be hashing. Just be hashing. But for us, we want to enter value. And this value, we want to declare this value as private. And then we want to declare the hash as public. And so that is now the difference. Now, so if you're doing it for production, in other words, in a real life setting, the hash that you get, and the way I was doing it, you have the ABCD. And this ABCD is converted to its field equivalent, and so on. Now, so for what I was doing is I was using Rust, first of all, to get the hash of this. And when you get the hash of this, it will be 2 raised to 254 bits, 256. So it's longer than the base that is used in Noir. Noir uses a base of 2 raised to 254. This is the base mod. The mod of Noir, when you're dealing with these big numbers, the mod Noir prefers when you're using the big integer, big num. The big num, if you're using big num, then the base for this is 254. That is what Noah uses. But what is produced as the hash is the length is 2 raised to 256. So it's larger than what Noah, the base of Noah. So then what you would do, you would then break it into limbs. And the big num gives a way of breaking into limps. So you divide it into 3, for instance, or 4, so that each of the small bits, which you are called limps, is lesser than the base. It's lesser than the base. You divide it into limps. So that's why I've said, if you're doing it for real world integration, then after hashing, whatever you get, since it will be bigger than what Noah uses as the base, has to be broken into limps. Then after that, we would then use compression just to now get the hash. So you first of all hash it somewhere and then break into limps that you have smaller values. So the ones you use, for instance, if you want to have prover.toml, you'll be using the limps for prover.toml. And even if you're writing your tests, unit tests, you will again be using your limps, but not numbers that are larger than the base that is recommended by Noah. Now, I think maybe we look at just an example to illustrate what we discussed. So as an example, we'll write a small Noah circuit that accepts a private image and then compute SHA-256 inside the circuit and assert equality with the public hash. Compile the circuit and run prover to create proof using the private preimage, and then run verifier to verify the proof. Now, I've not done all these steps, just did a few of this, but then we will want to do the rest of the steps later. You can see what I'm sharing, eh?
Yes, I can see.
Okay, this is my code from here up to here. This is the end. Below it, we have the unit tests. Now I've used 4 here, but you can change it to 32, 16, whatever you want, even here. So that will mean that you also change this point and several other points. Now, you've entered your value and I've said this is the circuit function. This is a circuit function from here. And after you enter your value, I've said convert raw bits into fields. That's what I said. That's the first thing this circuit does. Converts whatever you give it into fields. So to convert into fields, this is the logic. Let preimage mutable preimage field. So this will be converting into fields, and it's doing it from 0 to 1. So when I is I in this range, so that means it's doing I1, I2. That's why it's called mutable. That's why it's mutable here. So, you know, as I said, you give it A, B, C, D. So it has to change A into its equivalent, change B into its equivalent field, change C into its equivalent field, and so on. That is why it's I in this range. Now, after it has converted into the field, it hashes those field elements. That is what will then be hashed. Let the computed hash equals to this. Then after it has done the hashing, you now want to enforce equality. Just to be sure that the computed hash equals the expected hash. Now, how do you test this equality? That's why I now was mentioning the issue of Rust. You know, this one does the hashing, of course, on its own. It does the hashing. Now, so for me, I did using Rust because when I do Nago check, and get the prover.toml, I find that the prover.toml wants me to put some expected hash. So now Rust was giving me this because this one does not give me. This one, once I just say expected hash, it just hashed. It hashes behind the scenes. I cannot see what the hash is. So using Rust, I'm able to get the expected. Then I'm also able to get, now this one is just converting what was converted to bits, to bytes, the preimage. Those are those figures, the fields. I said, for instance, supposing A is 70. So this would be 70. If B would be 81, then this would be 81. If C would be 56 or 77, supposing D would be 30. So these are the pre-image bytes. And you get this by converting what you have to ASCII. It's ASCII equivalent. Then this is the expected hash. So that is where now I was referring to Rust at this point. And this point, I also said the value you're putting here should be less than the modulus recommended by Noir, which is, I think it's 2 raised to 254. So it should be less than. So that means the value you get, you can break it into limps. Then break into limps, and then you adjust this code such that it accepts limps. So such that it's able to accept limps. Now let me just again show you the one I was using to break into limbs, but you can always come up with a different one. One that can cut into 3, because Noah uses, last time I was using these limbs, I used 3 limbs. So it uses either 3 or 4, but the one I created here was I created for 2 limbs. Let me see. Cargo run. Yeah, 2 limbs. So this one is 2 limbs. This is the first limb, and then the second limb. So this number will have been bigger, but now it's cut into 2 limbs as this way. And then the pre-image bytes. This is what I want to hash. This is what I want to hash. So I was just converts each of them to ASCII. So A is equivalent to 97. B into ASCII is 98. C into ASCII is 99. D is 100. 1 is 49. 2 is 50, and so on into ASCII. So all of them are converted into. So when you talk of the pre-image bytes, these are what you're using as pre-image bytes. So you convert whatever you have into ASCII. And then you can do, this is the expected hash fields. So you're breaking your value, your hash into limbs. So it could be 2. In this case, I've done into 2, but you can do it into 3, into 4, and so on. So you can see how I was breaking into limbs. I've said from 0 to 16, this is the first limb, from 0 to 16. Then from 16 to 32, this is the other limb. So when you talk of 0 to 16, this program knows that 16 is not included. 0, 1, 2, 3, up to 15 included. And so when you talk of 16 to 32, again, 32 itself is not included, but we are talking of 16, 17, up to 31. And then you have those 2 limbs. There are several ways you can achieve this. This is not the only way to achieve limbs. I remember the other time also used a different way of dividing into limbs. But you can see I've said this is 0, and this is the first one. And you can now, even if you want to go into 3, you can just see how many times does 3 go into 32, and see how to change these values. Or if it's 4, again, you can ask yourself how many times, and you see how to change these values. So you have 4 limbs, and so on. So then you say print pre-image. Pre-image are when you convert to bytes, and this is where you're converting to bytes. The big unit to bytes. This is how we're converting that. And then you ask it to print the hash field, and then you can just copy and paste in our prover.toml. That is one way. The other way, you can want to work with your Noir circuit and give it some helper. give it some helper where the helper will be doing what Rust has done. What Rust has, it's not always that you have to have two programs, one giving you the hash and the other one giving you doing the Noah thing. No, you can just have one program. But now in that case, it means this program should be a bit longer such that you give it helper. Some helper functions that will be assisting it to do this bit. So the helper function that will be doing the pre-image bytes, converting what you give it into pre-image bytes. And then after that, hash the expected so that you're going to get the prover.toml. But you see this part is only giving the prover.toml. That is why I didn't want to add it into the other program. I didn't want to add it because that other program, its function was to do zero knowledge proof. I didn't want it to, again, give us the pre-image, then the hash. No, I just wanted to do the hash, but it's doing its hash in the background. It does not show me what the hash is, and so on. Now, so the Nago-Toml has no dependence. There's no dependence for the Nago-Toml, just like that. So this one I had not added, so I can just remove it the time being. Now, so the tests, the unit tests. Now, the unit test, when you are doing it, sometimes you need to use the real values. So for me, I did not use the real values. You may want to use the real values. For instance, the pre-image bytes. Now, this is just ABCD. This is correct. This is ABCD. A is 97, B is 98, C is 99, and D is 100. This is correct. The sky value of ABCD. But now I did not do the hash, but I wrote it such that it can accept. What I wrote here is correct. But in normal cases, you may want to use exact value for ABCD, the hash of ABCD. You want to use the hash value here, and so on. So that the assertion here, assert computed hash equals the expected hash. So you may want to write it such that you have the expected hash and the computed hash, and then you see whether the assertion is correct. So that is, but I didn't go that format. I didn't go the format. I didn't use that format. The format I used is what is in my, what is here, is what I used. The pre-image field I should equal to the pre-image byte I dot int. So that is what I used for the assertion here. But what I'm saying is you may want to use this part. So if you want to use this part for the assertion, then it means you must do what we've just done. Get the hash. You want to break it into limbs, and then assert what the expected, and then the computed, and see if they're correct, if they're equal. Now these other tests, I have 3 tests here. These again, I'm testing WXYZ. Their ASCII equivalent are this. Then again, as above, I test using pre-image fields I equals pre-image bytes I dot int. So if the expected equals that, so I say that the expected equals this, then it means the assertion is accepted. So there's no difference, even this one. Even this one is the same thing. So this one we're obviously going to accept. But if you wanted to use the hashed values, then you may come up with should fail test. So that is where you now intentionally, after getting the correct hash, intentionally change a value 1 digit and see whether it accepts. You get the correct hash, but then intentionally change 1 digit and see whether it will accept. So then in that case, that becomes should fail test. Because if you don't write should fail, then it will fail. But if you write should fail, then it passes. Oh, do you want the code? Can I send the code to you?
Yes, you can.
Okay. Let me just again get it. I don't know where it has gone to. Let me first of all, oh, I'm not sharing. Oh yes, I've seen it. So I can share this of, yes, this one of Noir first of all, if I share the Rust one. So I begin by sharing the main.nr. It says the message is too long, that it tries sending multiple. It says try sending multiple shorter messages. I thought it was short. I don't know. Oh, maybe because of the tests. So I can first of all send the message, the code itself, and then the test later.
Okay. Is it in the Noir Made Simple repository?
No, I did not commit today.
Okay. So I create another library, another directory for this one.
Yes.
Okay, let me do that.
It still says it's long. I don't know why it's long actually. Why is it longer? I've only taken the circuit without I've only taken the circuit without tests, and it's a very short thing. I don't know why it becomes longer. So this it appears this this chart accommodates a very short message, very short. No, it hasn't accepted. Same thing that it was rejecting. Have you seen it?
Just a moment. Yes, I've seen it. It's up to step 3.
Okay. So I can now send the yeah, it's up to step 3 where you're enforcing equality.
Equality, yeah.
That's the last statement in the circuit. When you're just now enforcing the inequality, now I can copy the tests. I'm hoping it will. Let me hope it sends all of them at once. Now this one again. To begin to say it's longer. But the other one, it was saying long and then accepted. I don't know. When does it become long? Now, create that and do Nago compile and see whether it accepts.
Okay, just a moment. This one. Where's the code? Step 3. Okay. So I have done up to the step 3.
Yes.
Okay, let me try to compile. Yes, it has compiled. I now have the target.
Okay.
So I do not go execute.
No, that one we need to get, first of all, try Nago check, because we need to.
Have the prover.
But now, what about we need
The values.
the hash and so on.
Yeah.
Just a minute. I want to send you
Okay.
the tests first of all. Just a few minutes. That's what I'm trying to see if I can do it. I think the only way I can do it is, first of all, I just commit it. Let me commit it and
Okay.
see.
Okay.
I've done it. I think it's now online. Maybe you can now download, clone it and see if you can get the tests. You have seen it, huh?
Let me see. Let me go to your GitHub and see.
And it's coming like a pull request on my own GitHub. It's coming like a pull request again. I don't know what I did.
Is it in the Noir Made Simple?
Yeah, I've seen the problem.
Yeah.
It has come like a pull request.
Okay. Maybe then you have to merge it.
That's what it wants. I don't know. Maybe I used master when I have
Main.
main.
Okay.
I've merged it. Can you see it now?
Let
It's
me
called, it's
look.
called Share 256.
Okay, let me
Pre-image.
look and see if I'll find it. Oh, yes, I can see it.
Yes.
Okay.
So you can
So,
even just copy, you can copy the tests, and then you input it in your yours so that we can you can try NAGO tests.
okay. Yeah, let me copy the tests. Yeah, I've done NAGO test and the tests have passed. They're good.
Okay. Now, so for us to do NAGO execute, we require those we require the limbs,
Yeah.
and there's supposed to be 3. The problem, the code I created has only 2. So I need to create for 3. Then maybe we now try it, but later. And maybe again, you can try it on your own. Try to get those limbs. So now when we get the limbs again, it will mean we change the code a bit so that it accepts the limbs.
Okay.
It will mean we make a few changes on the code.
All right.
For it to accept those limbs. Because the one we have here is not for the limbs. Let me just again look at it. The one I have here, when you do NAGO check, let me just see. NAGO check. What is that? Let's see. Oh, okay. Yes, when I do NAGO check, the property that I have, the hash, it only has one value. So what this one means, after you get that value, which is larger than what is required by Noah, you reduce it mod. You reduce it mod 2 raised to 254.
Okay.
That's what it means. This one, it means that. But I said for production reasons and for integration into real world, you don't need to reduce that mod 2 raised to 254. What you need is the value you get, the whole of it, you break it into limbs.
Are you sharing your screen? I can't see your screen.
No, I'm not sharing.
Okay.
Yes, let me just go back. So what I was saying is when you see what I've just shared now, the proper terminal.
Yeah.
So you can see the expected hash.
I have not seen anything. Oh, okay. I have seen it.
You can now see it.
Yeah.
The expected hash has only one value. So,
Yeah.
so,
It only has one
so that
value.
means according to the code we've written, it expects one value. So that means you get a value, you hash using Rust,
Yeah.
and then you reduce it mod 2 raised to 254. That is the value you enter here, the result.
Okay.
That's the value you enter here. But as I said again, if you are doing it for real world application, that is not the best approach. The best approach would be you get the hash, a longer value, that value which is longer than, because when you do a hash, you'll be getting 2 raised to 256.
Yeah.
So that value that you get, now break it into limps.
Yeah.
So that then means that we will redo our code to accept limps. So that now when you say nago check, it gives you spaces for limps. Yeah, it gives you spaces for limps if you do nago check. So that's what it means, that we then have to redo it. So that means maybe in our next class we'll redo this code
Okay.
to accept limps.
All right.
Yes. Now, so this is just the explanation of the code I've shared with you. It was coming up to step 3 here. Then what follows just explanation. But before explanation, I've said when you are doing this Noah's circuit, that it does hashing, the flow is that it gets the raw values, then converts them to fields. Then each field is then hashed. So the fields are hashed together and they give you the hash. So that is the flow, the typical flow in Noah, how it works. So the typical flow is that to accept raw bytes, you enter the raw values. Then those raw values will be the inputs. And these are the inputs we want the verifier not to get to know. So once you put these raw values, they are converted into field elements. Once they are converted into field elements, the resulting field elements are then hashed. Now, the essence of converted to field element is what I'm explaining on this slide, is that it's just to ensure that work is done over field elements, not raw values. That is what cryptographic primitives do. Now, the following is just explanation of the code I gave out, the code that we've just seen. And we were saying that this code was to prove that I know a secret image bytes with some value X. such that the SHA-256 of that value equals the expected hash. And this is the function. We already looked at this function. What I want is to explain what each of those lines do. So the first line, use depth. This line imports Noir standard library needed for hashing. So you must have it. Now, so I was, yes.
Electricity ilikuwa imepotea kidogo lakini imerudi.
Yes, yes. Yes, I was just explaining what each of those two which the lines of the code mean. The first line that we use depth, that is this importance is just to import Noah standard library that we will then be using for hashing. Then you have this other line. This one inputs a raw bytes. You could enter any word like secret pre-image, any word. So this is what where you input. It accepts any input. Then this int converts each of these U8 into field elements. So that is what it does. That's why it's there, just to convert the U8. Of course, you can change this U8 to any other that you want. But this part, its role will be to converting that to field elements. Then we had a line hash to field. Hash to field. This one is to compute cryptographic hash over the field array. Hash to field. So that is what that part will be doing. Then lastly, we had the part for assertion that enforces that the proof condition is binding. So that is what this part does. Now, this part is very important when you're writing your tests and even the proof atomic. If this part is not satisfied, then it means your tests, the inputs in the tests or the inputs in the proof atomic have a problem. So you have to again go back to your inputs and see that they are correct. If this part is correctly written, then it will really assist you in ensuring that what you are using in the proof atomic and what you are using in your tests are correct values. Otherwise, if they're not correct, then it will not, you get an error. So that is what that part does. Now, the input tests, I already talked about them. Of course, you are entering raw values like ABCD, and those raw values are converted to their ASCII equivalent. And then these ASCII equivalent together, all of them at once are hashed. All of them at once are hashed. So this is where hashing is happening. You hash all this at once. And so this is what you get. So that is very important because now, if you're hashing this, you see again, you're already confusing. You're already confusing the guy. Because this is what you get, what you had from the start. Convert it to this. And then after convert it to this, now hash. And again, it's very important is that once you've hashed, nobody, no genius can be able to get X out of the hash. This is not a function that you can get the inverse. There's no inverse of a hash. You can't get it. So that means that is a zero knowledge proof. And your values are very secure. The person can only see the hash, but will not get it to know what the X was. I think we can stop there, and what we can agree on is maybe in our next class, let's try to break that into limbs so that now we have Noah that is functional, not Noah, the proof atomic. The prover told me that we can run Nago execute. And apart from that, we can also extend it to JS and run the way we were running our proofs earlier on using JS. And also add the contract and verify our proofs using contract, the way we're doing it earlier in our other proofs. I think we can go up to that point and see what happens.
Okay.
Yeah, so let's try to see if we can go to the extent of using YARN proof in the JS.
Okay.
Yes, YARN proof, then again verifying the proof in the contract.
Hi.
Okay, so I think let's stop at that point.
All right. See you next lesson.
Thank you.